All right, so we'll get a couple things out of the way here. Probably easier for me to have the Canvas page pulled up. So we'll be working on with a couple files today under the in-class data folder, linear regressions. I'll be kind of working with this MBA shot and the social media data. My other sections are on Monday, Wednesday, Friday. So I did some different examples yesterday with them. I'll be posting that video on YouTube as well. So I'll kind of identify that, which one was the one we did in class, and then kind of the additional linear regression examples. If you just want more examples of me kind of running regressions, interpreting the coefficients, determining if things are significant, you'll have some more examples there. As we work through, we'll probably also do a little bit of a kind of review of those practice exams today. We'll just kind of start. As I work through those across all my sections, I'll be posting videos that kind of label which practice exam and which problems that's me working through, so that hopefully by the end of the week, we pretty much have every single problem on those practice exams worked through. We'll be kind of just doing some exam review on Thursday. So those, we'll cover some things in class, but some of the stuff that we don't cover in class, I'll be posting additional videos up there as you're kind of preparing for that final next week. Tentatively, it'll be available kind of Monday through Wednesday. I will be doing kind of a review session in my other sections, which I'll post that time and a Zoom link if you just happen to on Monday want to attend those. Even though it's not technically your section, you'll be able to do that. But the exam, so yeah, we'll be open over those kind of 72 hours from Monday to Wednesday of exam week. Once you start, kind of like the other exams, you'll have a certain amount of time. I've got it kind of set currently. I'm thinking about 2 hours there, so 120 minutes. So timing shouldn't be near as much of an issue, hopefully, on this exam. And it's going to be 15 multiple choice questions, 2 short answers with multiple parts. So looking kind of similar to the format of our other exams. Other than that, what else do I want to mention off the top? We won't be doing any more kind of online quizzes. So over the next day or so, I don't know if I'll get it done today, probably more likely it'll be posted tomorrow. I'll be dropping everyone's lowest 3 online quizzes. That's kind of what the syllabus state, actually, sorry, I'd be lowest 2 for the Tuesday, Thursday. So I'll get your online quiz kind of category grade up there on Canvas that reflects that I've dropped those lowest 2 online quizzes. I'll do the same thing for the Learn Smart. Since we won't have any more Learn Smarts, I'll drop the lowest and get that grade up on Canvas as well. And then as kind of the end of the week going into next week, I'll do the same thing for the Excel and the Connect assignment. So I'll be able to kind of show you a little bit more what this will look like on Canvas on Thursday. But if you see that start popping up with some different grades, things on Canvas, that's what I'm doing there to kind of show you what your grade in the online quiz category is with those kind of lowest 2 dropped. Okay. Any other questions for me before we kind of get jumping into things here? Yep. So there are 4. So there are 5 Excel and 5 Connect assignments. I drop your lowest grade, right? So they're not extra in the sense that if you've missed one of the first 4 assignments, your lowest grade is going to get dropped. So if you've missed one of the first 4, and then you missed the 5th one as well, well, now you have 2. One of them will get dropped, but one of them will still count as a 0, right? If you didn't do that. If you've done the first 4 of each kind, then yeah, the 5th one, if you don't do it, will be a 0, but it'll just end up getting dropped. Yep. Any other questions before we get going? Okay. All right. So let's start out with, I don't want to have these open. Open the wrong 2 because I was thinking of the ones that we did yesterday. So I'm going to use this one. And I think I will cover this social media one first. So I've got this social media data. It's kind of looks like a mess here. We'll go to this changes around recall tab. So this is kind of older data. So, notice it's kind of Facebook and Twitter were kind of the main ones. I think there was in the raw file, maybe some YouTube data, but it wasn't that great. So I've got this data in Excel, and it kind of looks a little bit difficult to understand, but we'll kind of walk through the variables that we're going to use. So this is a bunch of different companies, and these were recalls that they had, right? So some product that was recalled, we have the number of units that were recalled, whether or not it was a voluntary recall, kind of whether or not there was injuries that resulted as, result of the recall. And then we have whether or not it's a kid's product, just a one if it is or if it's not. And then we have kind of the changes in their social media following. Right? So this was kind of the changes 30 days before and 30 days after this recall, 14 days before and 14 days after, all the way up to just one day on each side. Right? So what I might be interested in is something like this, right? What was the change, right, in the number of kind of followers, or however we want to denote this, before and after the recall, right? So we've got all these changes. We've got, this recall occurring, but then we could say, well, maybe the number of kind of the increase or kind of expected the decrease in the number of followers depends on the number of units. So we've got all these recalls. Switch this over to the dot cam so we can have these both going at the same time. So I'm thinking about something like this. We can get the, it's a little bit dark here. Let me, maybe overexposed a bit there. So we're thinking about something like change in the followers is going to be our Y variable. And then kind of the X variable maybe is the number of units that were recalled, right? The more we would probably think that the higher the number of units recalled, potentially we would see kind of a larger decrease in the number of followers. But maybe this is kind of the idea of any publicity is good publicity, right? Maybe I actually see this slope coefficient as positive. That when I see these really big recalls, well, maybe I actually see an increase in followers because maybe people are interested in information. Oops, let's get this out of here. What was I saying? Oh, kind of anything that gets me in the media ends up having positive results. So let's just try to run this regression. Okay. So we go up here, data, go to my data analysis. We've got our regression tool here. We'll hit OK. My Y variable is going to be, here I'm going to select this as my label. We'll have to kind of change that because it just identifies like the one day before and one day after the recall. Well, maybe that's too small of a window. So maybe let's just go like a week, right? 7 days before the recall, how many followers did they have? 7 days after, right? So we'll use this kind of 7-day variable. Control Shift or Command Shift on a Mac, hit the down arrow. We'll select all the way down, to the very last observation for us. Click there. Oh, sorry, thank you. I swear I'm never gonna remember this. I'll show you how to do that again, right? Actually, since I messed it up, I'll go ahead and show you something else. So let's do, I'm gonna call this week around recall. So kind of this variable that we're looking at is the change in the number of kind of Facebook followers or friends, however we want to, I don't know exactly how we're calling this, but around that week before and that week after. So we go to that data analysis, go to regression. Our Y variable is this change around that week. Our X variable, go up here. We're just going to, for right now, include the number of units. Right? So this is the number of units recalled. Command Shift on a Mac or Control Shift. Hold that, hit the down arrow. Right? Goes down to the very last observation. We selected our labels. We'll hit OK. Oh, what is this? Not like. Oh, I started one of these in. I see. So this is going to be a unique one. Let me see where we aren't going to be able to select that label because it's in this kind of merged row. Right? So what I actually could do, just for the sake of what we're doing, I wouldn't expect you to do this. I'm just going to unmerge these so that I have the same number here. Actually, probably going to have to unmerge all of these. and then drag these labels down because I want to show you something after this. So go back to data analysis. Hopefully we fix this problem. So I've got my Y variable selected. Let me try selecting the X variable again, where I'm only starting at the label. Go down. Now we should be okay. So let's go here. Look at our results. First of all, if we're thinking about some things that we can interpret, the first thing we can look at is our R squared. So we've got this R squared here, which tells us the proportion of the variation in our Y variable that we're explaining with that X variable. So here, the proportion that we're explaining is what, 0.0005. So we're hardly explaining any of the variation in our Y variable, which means our predictions probably aren't going to be very good. Right? You know, the higher this gets, the closer to 1 this gets. If we could get this R squared to be 1, that would mean our X variables explain all of the variation, or that we're getting very accurate predictions. But it's not, right? It's still pretty low. So we go down here, though. Despite that, we can still do some interpretation. Okay? So here, the general interpretation of our coefficient on our X variable would be a 1 unit increase in the X variable causes the predicted Y value to increase or decrease by the, I'll move this box here in a second, by whatever that coefficient is. And I've misspelled it, but you can imagine this, right? So for our example, a 1 unit increase would be 1 more unit recalled, right? Not product, but 1 more unit, would predict that the change in, what was it, Facebook followers decreases by 0.001, right? So that might seem like a really, really small effect, but that's how we would do that interpretation. Now, one thing is, this is the effect of 1 unit, right? We'll just let, you can imagine, you know, one of the companies up there was American Eagle. I don't know what they were recalling, but I doubt it was something that was going to, you know, be super dangerous to people, right? So 1 more unit would be like if they recalled literally 1 pair of pants, right? I don't know, what is that really going to be a negative impact? Or what would the size of that impact be? Probably not very large, which is why we maybe see this be relatively small. Well, what if 1,000 units were recalled, right? Well, if this is the effect of 1 unit being recalled, the effect of 1,000 would be just that times 1,000. And now we see, okay, if there's 1,000 units recalled, we see a decrease in about 1 kind of follower there. Now, that is the interpretation, but we have to remember, well, can I even say that this is any different from 0? So if we remember, in all of these regressions, what we're doing is we're starting out and we're assuming that slope coefficient is equal to 0, because what we're trying to find is that anything other than 0, right? Is there a relationship between this X and Y variable? Well, in this case, with a p-value of 0.87, we only reject if the p-value is less than alpha. Well, our alpha values are typically 0.1, 0.05, and 0.01 are kind of our benchmarks. These would correspond to the 10% significance level, 5% significance level, and the 1% significance level. So here with a p-value of 0.87, that's not less than any of these. I can't reject at any of these levels. Well, if I'm failing to reject, what I'm really saying is I can't say that the relationship is anything other than 0. Right? The true relationship between the X and Y variable could be 0, or that there is no relationship. Right? So I can't really say that the number of units being recalled has any impact on the change in followers, right? So this might be either an indication that these aren't, being publicized enough, or maybe that any negative connotations are kind of offset by the fact that they're just getting their name out there. But this is an interesting finding. Right? Now we have a pretty small data set here, only 50 observations, but that's still how we would go about kind of analyzing this. Okay. Any questions here? Okay. All right. So let's go back to that changes around recall data. Well, maybe I want to include some other things as well, right? Maybe I want to include not just the number of units, but whether or not it was voluntary. So that's a 1 if it was, 0 if not. The number of incidents that maybe were reported, and then the number of injuries that occurred. So I'm going to go up here, go to data, actually, and also, because I want to show you something, also whether or not it was a kid's product, right? Maybe I think that if it was a kid's product, maybe there'd be more of an outrage or something. So go up here to my data analysis, hit OK. I'm still using that same y variable, so I'm going to leave that the same. But now I want to include, for my x variables, all of these number of units to instance, but also kids product. So I select these 4 variables, Control Shift, hit the down arrow. I'm going to scroll back up because I also want to include this. So if I hold Control, click over here, then hold Shift, I can select that variable as well. Now don't worry too much about what I was just saying with holding Control, because when I go to run this regression, it's going to give me this contiguous reference error. Right? So all that means is, in Excel, the only way I can run regressions is if the variables are right next to each other. Right? Not necessarily the y variable, but all the x variables need to be right next to each other. So I'm going to insert a cell here. I'm just going to move that kids product. So now all the variables I want are right next to each other. Okay? So now when I go to this data analysis, regression, I've got the correct y variable selected. I'm going to select these x variables here. Control Shift or Command Shift on Mac, hit the down arrow. Now it should run okay. Okay. So we'll go here. Oh, and I forgot. This is going to look a little bit weird. So I'll explain to you kind of what's going on here and why. I'm just going to get rid of this. So that voluntary variable, from the original data, I kind of got rid of some missing values. I guess this data set ended up being that every single observation was not voluntary. They were all zeros. So when it tried to run this regression, it looked at that and said, yeah, everything's the same. There's no variation. I can't pick anything up. So we can just act like we didn't include that because I forgot that all those ended up being 0. And anytime you see that in a regression, that's because Excel realized like this variable I can't use in the regression, so it just kicked it out. Right? So if we look at the R squared here, well, we've increased by quite a bit. So if we go to our first regression, and I'm actually going to rename this Reg 1. I'm going to rename our second regression Reg 2. Okay? So in our second regression, where we included several other variables, our R squared, the amount of variation we're explaining in the number of followers change is about 4%, right? Or the proportion of 0.04 compared to 0.0005 before, right? So these variables that we added into our regression look like they explain a little bit more of that variation. So it looks like they have some sort of predictive power. So our R squared went up by quite a bit. We kind of go down here. This is going to be a little bit screwed up, but we can kind of work around that. So now if we look at the number of units, it's no longer a negative effect. It's now slightly positive, but that p-value is still so high, we can't say this is any different from 0, right? We would fail to reject that null hypothesis, and it looks like we'd fail it for the number of units. Let me see. We could actually come up with, well, this test statistic's pretty low, so our p-value will be pretty high here. This p-value is still pretty high, 0.2. None of these are actually going to be statistically significant. Okay? So it looks like none of these variables actually can we say that we reject the null for, right? Because they all have p-values that are above 0.1, 0.05, and 0.01. Okay, so we fail to reject the null for all. But that doesn't mean we can't still interpret them, right? So let's think about like the kids product one, because it's a little bit different than what we were doing before. Well, now what's a 1 unit increase in this x variable? Well, this kids product variable, if we go back, well, that was just a 1 if it was a kids product and a 0 if not. All right, so just 1 if it was a kids product, 0 if not. So when I make this interpretation, a 1 unit increase would just be a kids product relative to whatever that 0 category is. So a kids product relative to a non-kids product, right? Not productive, product, would predict that the change in followers increases by what, 276,523? I mean, this seems pretty wild. So if it's a kid's product that gets recalled, we actually see a pretty large increase. Like that's the interpretation. However, we say there's an increase, but we can't actually say that with statistical significance, right? We can't actually reject that null hypothesis because the p-value is still quite a bit above 0.1, okay? But we can still make those interpretations. So another one that we could do, let's do an interpretation of the intercept, right? So the intercept interpretation is if all x variables are equal to 0, the intercept is the predicted value of our y variable. Okay? That's kind of the general interpretation that we've been working with. So here, the interpretation would be weird, but it would be like a recall of 0 units had 0 injuries, 0 reported incidents, and not a kid's product would see a what? Would have a change in followers of negative 114,906, right? So it's kind of a weird interpretation. Like, we know that if we have a recall, this really doesn't make a lot of sense, right? Often that interpretation of the intercept will be for a situation that can't actually happen. But the idea here is that if we have a recall, if I'm trying to estimate, let's say, the number of units, the relationship between number of units recalled and change in followers, right? Those are my x and y variables. If I had the data, it probably looks something like this, right? Where anytime I see something recalled, I likely am not going to see just 0, 1, 2 units. It's likely going to be a pretty large batch of units. So when I see all the data over here and I try to come up with this line of best fit, well, it's going to end up with a negative, it's going to end up with a negative intercept, right? Or it's going to end up, when I'm making that interpretation, it's going to be for a situation where I never even see the number of units recalled be this low. But that's still how I interpret the intercept, because it's still kind of like, well, this is where our starting point's at. And just because I don't ever see any x values in this range, in order to make the accurate predictions here, I need to be able to allow that intercept to be negative. Can you imagine, like, let's say I didn't allow the intercept to be negative just because it didn't make sense in the context of the example. Well, now when I come up with, I drew that a little bad. Now when I come up with my line of best fit, notice for all these observations, my errors are going to be a lot worse than what they were before, right? I'm making a lot kind of larger errors. Right? So that's why sometimes the interpretation of the intercept doesn't make a whole lot of sense, but that's still how we'll interpret it. Right? And conceptually, that's how we want to think about it. It's kind of the starting point. Any questions on anything here? So I don't know. I thought that was kind of an interesting data set. Ahead of time, I didn't know that a whole lot, kind of going into sometimes running these regressions, you might think that there's a lot of relationships between your x variables and that y variable. Here we can kind of see, well, first of all, we're missing a lot still. There's like, what, 96% of the variation in that change in followers variable that we still can't explain. So our predictions probably aren't going to be that great. The variables that we had to try to predict that change in followers apparently don't have a very large influence, right? Or they aren't highly correlated with our y variable. And that's okay. Sometimes when you run this regression, you'll see that none of your variables are significant, right? It just means you have to kind of keep looking for what matters, right? Look for that rest of that 96% of the variation that you still can't explain. Okay. All right, so the other one that I had that someone reached out at me and was asking about, and I'll try to answer their question, but we might not be able to answer it quite perfectly, right? So I'm gonna zoom in on this just so we can see a little bit better. So this is a bunch of NBA shot data, so it's like every shot that's ever occurred in kind of these games. You've got to kind of got the current score, the player, how many points that shot was worth, etc. So the kind of idea that was emailed to me was, could you figure out if someone's like a clutch shooter, right? Well, probably could take a lot longer and come up with a really good regression to kind of analyze that exact question. But we'll kind of do the best that we can for the context of this class. So one thing I wanted to show you was what happens if we have a y variable that's a 1 or a 0. Right? So the regression that we're now going to be thinking about here, or at least what we're going to start out with, is, was the shot made, right? And that's just a 1 or a 0, right? So was this shot made? And we could think about, we're trying to look at maybe like how clutch someone is. I'm going to go over here. Where was it? Oh, here it is. Kind of having what that point gap was, right? So kind of seeing what the point gap at the time was. Now, it's not the perfect measure, but at least tells us, you know, on average, our players kind of clutch. We could analyze this player by player. It's a much longer thing, but just to kind of get at this, what was the point gap in the game, right? So maybe if the game is closer, maybe people are more likely to make that shot if on average these players are clutch, or maybe if that point gap is wider, well, maybe they're trying even harder to kind of come back in the game, you know, whatever the story wants to do. But we don't know what this estimate's going to be, but we can use a regression to determine that. So I'm going to go up here, data analysis, regression, okay. So my y variable that I want is just whether or not the shot was made, right? We have that 1, 0 y variable. So I'm going to control shift, hit the down arrow, select it, the arrows again. And what was the one I was interested in, right? If I go over, looks like it was the point gap. So I'm going to control shift and select that. Okay. Got my label selected, put it on a new worksheet. Zoom in, excuse me, so we can see this. Notice the r squared here is what? Move the decimal 5 places to the left, so 0.00006. So we're hardly explaining any of the variation in whether or not that shot was made by using that point gap. And sure enough, right, we kind of can't say that it's any different from 0 here because the p-value is much larger than any of our alphas. Okay? So just kind of doing this naive regression, right, we don't really pick up a whole lot from that. Call that reg 1. Right? There's really not, you know, a whole lot of variables here to interpret. But if we were to try to interpret this, what would a 1 unit increase in our x variable be? Well, if the gap in kind of the shooter's team and the opponent team, if the difference in the score of the game goes up by 1 point, we'd actually expect the probability that the shot is made. Right, so here it's kind of weird because usually it's the increase or decrease in the units of that y variable. Well, when your y variable is just a 1 or a 0, the units are really like increases in probability. Right? So anytime we have a y variable that's a 1 or a 0, the interpretation of our coefficients, we still do it the same way. It's just that when we talk about the predicted increase or decrease in our y variable, it's not in the y variable's units. Well, it still is in its units, but its units are now not like dollars or inches. It's increases in the probability, okay? Moving from 0 to 1. So it looks like maybe on average, right, there's a little bit more kind of clutchness that occurs when games are close. Right? But you could also go up here and just think about, well, I bet there's a lot of things that matter. So I'm just going to throw the kitchen sink at it. I've got things like the player's height, weight, whether or not they were on the home team, the attendance of the game, the average kind of field goal shooting percentage of the player. And if I can control for a bunch of these things, we'll get a regression that really is pretty powerful. So if I hit OK on this regression, my y variable, have that shot made still selected from my earlier regression. But now for my x variables, I want to include shot distance, the angle, whether or not it was a 3-point shot, all this different information. So control shift, hit the down arrow, got all my x variables selected. Oh, what did I do wrong here? Why is this going down further? Oh, I copied it over. So we'll go to the same one. I think I accidentally just bumped my down arrow a couple times. Oops. Why is this not like this? Let's try this again. So we'll go shot made. Okay, that's good. Now we want all these other variables. Okay, I see what's happening. So anytime you have some missing values, this is kind of a good data cleaning kind of way to do things. Anytime I have missing values and I hit that down arrow, it's going to stop kind of prematurely. So hit cancel here, go up to the top. And what I can do is I'm going to go to the very last variable in my data set, hold Control and Shift, hit the over, then the down arrow. That should select my entire data set. I'm then going to make sure I've got that filter turned on so that when I go to the top, if I can get my mouse up here. Now every variable has kind of one of these little arrow drop downs on it. So what I can do is look and see, okay, what are all the responses for this variable? Well, this one is just 0 and 1. We go to that shot distance. Well, this is going to have a bunch of values, but if I scroll all the way to the bottom, what I can find is, oh, there's some blanks in here. Well, I can't use an observation that has blanks, so I'll deselect everything, click on the blanks. Okay, looks like there was 3 bad observations here. For the sake of what we're doing, we're not going to try to complete them. We're just going to get rid of them from our analysis. Okay? We then go back to that shot distance filter, select all of them again. Now, hopefully, we've got everything kind of working here. But I could play around with the other ones, make sure that there's, okay, no blanks here, no blanks here. I think everything else, hopefully, should be good. Oh, so this field goal mean has some blanks, so I'm going to deselect that. Click on the blanks. Okay, 1 bad observation. Go over here. Select everything again. Attendance, no blanks, total seconds. Looks like we're kind of good here, hopefully. Let's check the height and weight. I don't think there should be anything. All right. Now let's try this again, right? We've gotten rid of some of those problematic observations. So we go to the Y, we select that shot made variable, X range, we're going to hit this, go back up. So we have the shot distance all the way over to what? The height and weight of the player. Select that. Okay, now we got it to work, right? So anytime you're running this regression, and it's giving you kind of errors that your X and your Y variables don't match up, it's usually probably because when you're using that Control Shift down arrow to kind of use that shortcut, there's probably some missing values in there. So that using the filter tool is a good way to find those. So we're going to zoom in on these results and get a little bit of interpretation to kind of see really what the power of our regression is. So we've increased our R-squared quite a bit. We're still not explaining a ton of the variation in our Y variable, but using all the X variables that we included, right? We now not just have the point gap, we've got all this other stuff. We're now explaining about 5% of the variation in that shot made variable, right? The proportion of 0.05. So we've increased it by quite a bit. We've got a lot of observations here. So I'm gonna close this real quick so we can look at everything. So one thing we said last class, we could kind of write an if statement over here to determine which of these variables are significant, right? Or we can just kind of look at it, go through with our eyeball. So let's say maybe I just want to see whether or not this is significant at any level. So as long as the variable is significant at the 10% level, so the p-value is less than 0.1. Well, this one, I definitely can reject the null. Remember the null being, let's get this up here. The null being that there is no relationship. I can reject that for shot distance, shot angle, whether or not it was a 3. Here it looks like the period doesn't matter. All right, so as the game kind of goes on, or period, the quarter of the game goes on, doesn't have any influence on whether or not I'm more or less likely to make that shot. The point gap actually doesn't matter. Right? The field goal mean of the player in the rest of the season matters. That makes sense. Attendance, surprisingly here, doesn't have a large impact. And then kind of home team, we could say has a significant impact. Height does, but the weight and the total seconds remaining in the game don't seem to have a large or significant impact on whether or not that shot is made either, right, on that Y variable. So we could go through and make our rejection decisions just based off this p-value column. Now, one thing that might be interesting to do is, which is the most interesting one here, I'm going to choose shot distance here, okay? So I believe shot distance, if we go back, is measured in feet here, right? So our interpretation would be that if the shot is taken 1 foot further from the rim, that the probability that the shot is made goes down by 0.01, which might not seem that large, but right, probabilities have to be between 0 and 1, so that's a pretty good, 1% decrease there, right? Now, not only is that the interpretation, but when we have multiple variables on the right-hand side, the interpretation would be a shot taken 1 foot further from the rim would decrease the probability I make the shot by 0.01, holding everything else constant. So the thought experiment would be holding the shot angle, right? 2 shots taken at the same angle from the rim, 2 shots that are both either threes or not, taken in the same period. The point gap of the game was the same. The field goal mean of the player taking the shot was the same. The attendance of the game was the same. They were both on the home team or not. Total seconds remaining in the game were the same. They both were the same height and weight, but one of them took a shot from 1 foot further from the basket. The decrease in the probability of they make the shot would be 0.01. So when we start to be able to include a lot of control variables, we're getting like otherwise identical scenarios, but just one little unit change for one of them, and we can understand what that predicted increase or decrease would be in the Y variable. Okay? So a lot more power when we're able to have a lot of control variables like this. Okay? Any questions on anything there? Let me think about what else I want to say. So we've gotten pretty much just kind of some different interpretations, some different problems that you might run into in Excel. We interpreted the intercept. We look at p-values. So one other thing that we could do, then I went through this last class with an example, but kind of do something similar here. So what if I wanted to predict the probability that a player makes a certain shot, right? And I would have to have like a paragraph of this information for you. But let's just say, right, that I want to think about a hypothetical kind of shot being taken and the probability that it's made. Right? So maybe, and I'll double check on this. So let's see, I think that shot distance variable, I'll double check that it's in feet, but I had created it. Yeah, so this is in feet. So let's say that the shot distance was, I don't know, 20 feet from the rim. The shot angle was, and let's look at how these angles are measured. So I don't know, there's something about the angle system. We got what? Kind of around 1. So I don't know, 1.1, however that angle is measured. It's not a 3-point shot, so we'll put a 0 in there. It's the second quarter of the game. The point gap is currently, I don't know, 4 points. The field goal mean of the player shooting is, he's on, maybe he's a, if I can get my mouse, there we go. Maybe he's like a, 54% shooter or something. The attendance in the game, well, what's an attendance that makes sense? For our hypothetical, looks like we've got things in the, around 20,000. So we'll just kind of say 20,000. So 1, 2, 3. Let's say he's on the home team. So this would be a 1. Total seconds remaining in the game. I don't know, maybe it's towards the end of the game. So we'll say there's only 200 seconds left. The weight of the player, I don't know, let's say they're 210 pounds. And they're, what would make sense? 72 would be 6 feet tall. So we'll do that. They're 6'6" or 78 inches tall, right? So we got this hypothetical person. So what we would then do is take each coefficient and multiply it by this person's X value. Oh, why did it do that? Okay. So we'll be able to see these. So for the intercept, well, we're just going to have to say, the intercept you just added in, right? It's not multiplied by anything. If we think about our regression equation, right? We're trying to come up with predictions about what's the predicted probability of the shot being made. And we have the intercept, we just add that in. And then for each other variable, we take that coefficient, maybe this is the height of the player, and we multiply the coefficient by the X variable, right? Or the value for that X variable. So we're just going to go through and do that for every single one, which is take that coefficient value, multiply that by your hypothetical value for X. We're then going to do that for every single variable that we include in our regression. And then once we're done, to come up with that predicted probability of making the shot or the predicted Y value, we're just going to add all those up. That's essentially what we wanted to do with our regression equations, be able to make predictions about our Y variable. Okay. So once I add all those up, I get that for this particular shot, there's about a 42% chance the player makes it, or the probability that the shot is made is 0.42. So this is kind of how we would come up with predicted values for Y. And probably the easiest way to do it in Excel too. Any other questions on this linear regression stuff in Excel? We'll probably move on to some kind of a little bit of exam review for the next like 30 minutes or so here. Okay with this? Questions? All right. So like I said, I have two other examples where I just worked through a couple other data sets. I actually didn't do as much with prediction on that one. I did a little more interpretation, kind of the structure of how we add in variables and think about the R squared, but all stuff that we did today. You can just see additional examples that I'll post on YouTube as well. I think there we did, and I'll post the ones I did with my other class. I'll post those regressions, the Excel files that go along with those regressions. I'll put them in the in-class data linear regressions folder. So that is traffic data we looked at, and we looked at some shark attack data in those sections. Okay. All right. So let's go to final exam practice form A. Right? I think I have this labeled as spring 2021. So it's the same one that I'm using for you guys. Just kind of rotating some old questions. So this is all kind of older stuff. We've done a lot of linear regression today, so I don't want to kind of focus too much on that. So we'll start with kind of going back to the very first kind of stuff that we were going over after the last exam, which was two population examples. So just as kind of a broader, I don't know how many questions we'll get through today, but kind of a broader thing that I want to go through is we've got a couple different types of scenarios we can look at. And we want to make sure we keep straight which distributions that we're using. Right? So anytime we've got two sample means, and we know the population variance, this is a scenario where we can use that standard normal or that Z table. Okay? So this is when we know the population variance. Anytime we're looking for the differences in two sample proportions, whether or not that's confidence intervals or hypothesis testing, use that standard normal. These are the only two scenarios on this upcoming exam for which you'll use that standard normal distribution. Every other scenario, you'll use the student T, which would be examples where you've got the difference between sample means, but you only have sample variances. You're looking at a sample difference, and all you have is kind of the sample variance there. Actually, sorry, this shouldn't be D bar if I'm notating it correctly, just kind of S squared for D. And then kind of one other example, although we're not really like looking p-values and stuff up like that, but when we're looking at those coefficients, we said those actually also come from a student T distribution. Okay. So those are our 5 different types of examples for this upcoming exam. 2 in which we use a standard normal, the other 3 in which we use a student T distribution. Okay. Now, one way to really make sure that you don't get that wrong, anytime you see proportions, automatically standard normal distribution. Anytime you see that you have a known population mean or you see the sigma squared guy, standard normal distribution. Anytime you see an S, right, notice these are all S, so sample variance, standard error, but sample standard error, all use the student T distribution. Okay? So it's kind of something that might be good to like have written down going into the exam or as you're kind of studying for the exam, have those kind of 5 scenarios and which distribution you use. So we look at this first one. This might be a little too big, we'll see. No, that's good. And we've got this idea that Indiana is a far superior state than Ohio. I think I left off kind of exactly what this was in the explanation, but here it is in the problems. So we're looking at BMI measures, okay? So we take 40 individuals from Indiana, and they have an average BMI of 27 and a variance of 25. You take 50 individuals from Ohio, they have a, average BMI of 29, but a variance of 36, right? Sample variances. So if we've got sample variances, and we want to find the difference in sample means, student t distribution. So I'm probably going to need my student t table. So once again, these would be good things to have printed out probably or pulled up as you're kind of studying for or going through this exam. So we've got our student t table pulled up now. So the very first question is, what's the confidence interval for the difference in these two sample means? And kind of notice here, I'll make sure that I identify which group is 1. Indiana was group 1, Ohio here, group 2. Well, first of all, maybe I also want to have that formula sheet ready. So here's my 3 confidence interval equations, right? When I'm looking at the difference in statistics. I've got the difference in sample means, but I don't know the population variance. I have the difference in sample means where I've only got sample variances, right? So so this is going to be the equation we need to use. Really, it's just a matter of plugging the values in, right? I can plug in my 2 sample means. I was given the sample variances, given the sample sizes. The only other thing I need to do is find this t-value. Now, I could calculate this guy right here as kind of an intermediate step. This represented the standard deviation of the differences in my sample mean. So I could calculate it ahead of time and then plug it in, but I could do it all at one time as well. But the missing piece is this t-value. So here, we're kind of reminded the degrees of freedom is not simply n-1. It's this big, complicated formula. But I need the t-value that gives me alpha over 2 on each side at that degrees of freedom. Okay? So what I'm thinking about here, I needed a degrees of freedom, which I told you I will be giving you. Like, so on the exam, I'll give you like this assumed true degrees of freedom. Okay? So we've got an assumed true degrees of freedom of 50. At the 99% confidence interval, our alpha would be what value? 0.01. So our alpha, we're kind of thinking about, I'll write some things down as I'm saying them just to maybe help as you're kind of going back. If alpha is 0.01, well, remember, for a confidence interval, I'm thinking about I have half of alpha on each side of my confidence interval. So alpha over 2 here is 0.005. I was told my assumed true degrees of freedom is 50. What t-value would give me that area of 0.005 in a tail? Okay. So I'll go to my student t table. I want 0.005, so this last column, what degrees of freedom? 50, so I got to scroll down a ways. Keep going. Looks like that's right here. So 2.678, right? Once I have that t-value, it's really, I mean, I can write this out, but it's really just a matter of plugging that 2.678, right? So we found it was 2.678 standard deviations above, 2.678 standard deviations below. That's already kind of built into my confidence interval equation, right? I add to get the upper bound, I subtract to get my lower bound. But it's really just a matter of plugging my values in now and then being able to kind of get it entered into my calculator. Okay. So let's look at the answer. I think I just bolded the answers. So, you know, if we wrote this out, what would this look like? So I guess I will kind of try to write this out for the context of this example. So we've got all the numbers here. So let me kind of try to do this simultaneously. So the first thing that we're going to want to do using that formula sheet was just take the difference between my 2 group sample means, right? So for me, that would be what? 27 minus 29. I'm then going to add or subtract to that t-value, which we found was what? 2.678. And then we're going to multiply by the square root of each group's sample variance over that group's sample size. So what? Sample variance for group 1, 25 over 40. And then 36 sample variance over 50 sample size for group 2. I just remember plugging my values in there. And I'll blow us up in 1 second. But I want to kind of point out, let's not lose sight of what we're doing. we're using our sample statistic, which now is the difference in sample means. Remember we said we can think about this as kind of like the sample difference that we found? So that sample difference I found was -2. So I'm basing my confidence interval around that. So I'm going to go 2.678 standard deviations to the left and to the right of that sample difference I found. So -2 should be smack dab in the middle of my confidence interval. -2 isn't even in this confidence interval, D, right? So I can rule that out right away. I might not be able to recognize it immediately, but -2 is like 0.8 away from -1.2, but it's what? 2.2 away from -4. So it's not in the middle of this comp. So I can rule these two out right away. And from there, it is in the middle of these two, but I have to actually just have to do the computation. Okay? So once I kind of identify that confidence interval equation that I need to use, really the only hard part there is remembering to figure out what alpha is, divide alpha by 2, and then looking up that t-value. Okay? Got someone in the chat. Do you always do alpha over? So when we're building confidence intervals, we're always taking alpha over 2, right? Because with our confidence intervals, we really can't make we're not making directional statements, right? We're just saying what could be the true value of this difference that I'm interested in. What's the true population difference based off the sample evidence I found, right? We're not really testing anything here. We're just kind of building this range of potential values. So you'll always divide alpha over 2 when you're looking at a confidence interval, which if we look at the formula sheet, it kind of reminds you that you're always dividing alpha over 2 here, okay? It's a good question. Any other questions before we kind of keep moving through a few here? Okay. So the next thing that I want to do is, what is the test statistic for the hypothesis test that Indiana has a lower BMI than Ohio, right? So in this one, I identified what that known alternative hypothesis were for you. But if we're thinking about, we're testing for whether or not the BMI is lower in Indiana. So if we remember, Indiana was our group 1, right? So if we're thinking about that, what? Indiana is lower than Ohio, but I want to write this out as a difference. Well, I'd have to write this out, subtract this from both sides, and I'd have Indiana minus Ohio is less than 0, right? Because the only way that Indiana is smaller is if that difference is negative. Right? So that's kind of where that known alternative hypothesis come from, right? But I'm giving that to you here. So what type of tailed test do we have? Huh? So what's the only time we would have a two-tailed test? What would we have to see in the alternative hypothesis? A not equal to sign. So if we look at the sign we have in the alternative hypothesis, we have a less than sign here. So we have a less than or a left-tailed test. Or as someone said in the chat, it's a one-tailed test, right? But it is a left-tailed. We can go a little more specific there. So remember, the type of test is based off the alternative hypothesis, the sign in that alternative hypothesis. So we have a left-tailed test, which doesn't really matter for calculating the test statistic, but that's what we're going to kind of use moving forward. So to calculate that test statistic, we go to our formula sheet. We basically have 3 test statistics here. Here's one for proportions. I think that one's a little bit easier to identify. We're not dealing with proportions, so we're not using that one. We have the difference in sample means, but we don't have population variances. We only have sample variances, so this is the guy we're going to use. This should be relatively easy. I mean, if you're asked for a test statistic, really it's about identifying the correct formula, right? Identifying the type of problem you're dealing with. Are you dealing with sample means? Are you dealing with sample proportions? Do you have known population variances or do you not? Right? Once you get that, it's just what we had like 27, 29. We had the variances and the sample sizes. It's really just going to be a matter of plugging everything in. In fact, one thing that's kind of interesting to think about, I don't know if this helps anyone, but if I've got my confidence interval, really what this represents is that standard deviation of the difference in my sample means. Well, notice this is the numerator in my test statistic. This is the denominator. Because when we're looking at these difference examples, I always told you that I'm always going to use that assumed true difference of 0. So notice those formulas that I gave you on that formula sheet, they don't have an assumed true difference because I'm not going to give you any other value than 0 on the test. So it's just a matter of plugging our values in here and getting that correct test statistic. Excuse me. Now, one thing to remember, I'll write this out because I think it'll help here. So here's my test statistic equation when I have the difference in sample means and I only have sample variances, right? So what this denominator represents is a standard deviation of the difference in sample means. So this denominator, right, variances and sample sizes can never be negative. This is always going to be a positive value. So the sign of the difference I found tells me the sign of my test statistic, right? I always know that the denominator of my test statistics, the denominators are always positive. So that numerator is always going to tell me the sign of my test statistic. Here, the sample difference I found was what? 27 minus 29, so -2. So my test statistic should be negative. So if I look at my possible answers, I can rule out A right away. I know it has to be one of these negative values. Really from there, it's just a matter of plugging those values in. So if I do that real quick, I'm going to have what? -2 over the square root of, what did we have earlier? So it's 25 over 40 plus 36 over 50. So I should end up with about -1.725. Okay? So once you plug those values in, you should get about -1.7 there. Okay? So those test statistic ones, I think, should be relatively easier questions on the exam. It's just a matter of kind of making sure you know what type of example you're looking at. So here's where we can start to combine, now that we know it's a left-tailed test, with this idea of, okay, let's say the degrees of freedom, I told you, assume it's 50. Same thing I told you, earlier. We had to assume true degrees of freedom. I want the 95% confidence level. What would my critical value be? So the 95% confidence level, what would my alpha value be? Yep, so my alpha is, I'm just writing these down, 0.05. Okay. If I want a critical value and I've got a left-tailed test, what's the sign of my critical value going to be? Well, my critical value, remember, I'm looking at that student t-distribution. My critical value for a left-tailed test is just what t-value would give me this alpha of 0.05 in this lower left tail. Right? So I know that if it's on that left side, it's going to be negative, right? Because that student t-distribution is centered around that mean of 0. So I know it has to be negative, so right away I can rule B out. Right? I want 0.05 in my tail, right? At degrees of freedom of 50. So I go to that student t-distribution. The area I want in my tail is 0.05. My degrees of freedom is 50. So 1.676. Now here's where you don't want to make an error. So it's 1.676, the value I see on the table. But remember, on this student t table, it's always looking at the area to the right because it just wants to show you all the positive values. Well, everything would be the exact same on the left side of the distribution. It would just be that all these values would be negative. So I can find the value using that student t distribution, but then I need to remember, oh yeah, it's 1.676, but I have a left-tailed test, so my critical value is negative. Any questions on that before we keep moving here? We're okay? All right. So I believe the next part of the question then said, assume you found a test statistic of -1.55. So my test statistic was -1.55, right? Which, if I'm thinking about making rejection decisions, once I have that critical value, I only reject if the test statistic is more extreme than that critical value. In this case, a larger negative value or to the left. Right? I reject if the test statistic is to the left of the critical value for a left-tailed test. I would reject if it was to the right of the critical value for a right-tailed test. Or I kind of always just say just more extreme or larger in absolute value. It's not here, right? It just fell short, right? So At the 95% confidence level, that critical value is negative 1.676, and we fail to reject, or we do not reject. Okay. Any questions there? Kind of did that in a couple different parts there. But kind of notice how the flow of these questions. I'll have to give you, I'll give you a lot more assumed things because I don't want there to be cascading errors. So first of all, I'm always going to give you the assumed true degrees of freedom in situations like this. But even after you calculate the test statistic, I might give you assume you found it was negative 1.55. Once again, don't read into these values at all. Sometimes I will choose them for reasons completely other than that they are close to what the real value is, right? In fact, sometimes I'll often choose things that aren't close to the real value. Okay. Well, we got 15 minutes. Let me see if that question here. If it was different than, would the critical values be? Okay. So let's say we had this exact same problem. This is good. Exact same problem. But instead, we had, I don't know. I'm not going to hunt for oh, it doesn't like that. It's got some built-in shortcuts. So let's say I go and insert a not equal to sign. Here it is. So, and then this would be, so let's say we want to do the exact same thing, but we have a two-tailed test. I want the same confidence interval, everything, right? So if I want the 95% confidence interval, but I've got a two-tailed test, my alpha is still what? 0.05. But for a two-tailed test, I need to find the t-value or the critical value that gives me alpha total in the tail, right? So it's very similar to confidence intervals for a two-tailed test, right? We're going to have half of alpha in each tail. So this is what, 0.05 over 2, so 0.025. And then we have a negative and a positive critical value, right? We'll have a pair of critical values. So it's going to be a t-value, but right, our critical value. So now the area we want in the tail is 0.025. So we go to that table, 0.025 at degrees of freedom of, we were given us, I think it was 50, right? 2.009. So now our critical values would be positive and negative 2.009, right? So kind of notice when we want to do a two-tailed test, it almost makes it more difficult to reject the null, because think about when we were given that assumed true test statistic of negative 1.55 here. Notice now our rejection regions kind of to the right of the positive critical value, to the left of the negative critical value. Notice we are much further away, right? When we had that left-tailed test, negative 1.55 is a lot closer to negative 1.6 than it is to negative 2.009, right? So two-tailed tests almost make it like more difficult to reject the null, because if you think about it, at least when we have a direction that we know that we want to go in, we don't have to worry about any results on the other side. So it's almost like we've shrunk our distribution down just to like half of the, right, just the area to the left of 0, because nothing to the right of 0 matters, right? When we have a one-tailed test. But with a two-tailed test, now both sides matter here. So you kind of like, there's just more possibilities for which we could reject, making it a little bit, kind of less likely that we reject if we're looking at a one versus a two-tailed test. Did that answer the question? Let me see. It was different with the critical value. Yeah, so we'd have pairs of critical values. That's the only situation when we're doing hypothesis testing where we divide alpha by 2 is for a two-tailed test. And we kind of saw how it would change the results. Okay. So that was a good question. So don't ever be afraid to ask questions, especially as we're doing a review. I'm not doing this for myself, right? Like the review part is really for you guys to ask questions, or if there's something that you're kind of stumped on, make sure that, or if we work through a problem, like, well, yeah, but what if this changed, right? This problem seemed a little too easy. What if this changed? Those are probably really good questions to ask. So we had that as our answer, right? We could deal with the proportion one, but I think we'll save that for next class. Let me see what's down here, some linear regression stuff. Let's keep working with that student t distribution. We'll do a slightly different example. So let's say we've got, we want to know what happened to calorie consumption before and after McDonald's started posting calories on their menu. So we've got 42 individuals, and we have the recorded calories before they posted the calories on the menu and the after, right? So for every person, we take this difference or calculate this difference variable, which is the calories after minus the calories before. So anytime we're thinking about, like, I've seen a lot of these issues when people were asking me for help on the Excel assignments. Always take the newest time minus the older time. So after minus before, right, is how we're going to set these up. So I've got this sample difference of -50 and a sample variance of 22,500. And I've got what? I want to know whether or not calories have decreased, right? Calorie consumption has decreased. So I'm thinking about, is this average difference less than 0, right? Because if calories are kind of lower after the posting, this difference would be negative. So I've got, once again, another left tail test. Right? So if I wanted to calculate the test statistic, this should be one of the easier problems on the exam. So I go to my formula sheet. I have these confidence intervals and test statistics up here, but we also had the confidence interval and the test statistic for when I'm looking at the sample difference. Well, it basically goes back to almost like the one population sample mean examples. So I have 3 values to plug in here. The sample difference I found, the sample variance, and the sample size. So go to my problem. I'm going to take that -50. I'm going to try to write this down as I say this. So if we're just plugging things into that formula sheet formula, I've got -50 divided by the square root of the variance over my sample size, which I think was 42. Well, remember, once again, my denominator is always going to have positive values in it because it represents some type of standard deviation. In this case, a standard deviation on the sample difference variable. So my numerator is going to tell me the sign of my test statistics. So right away, I know it has to be either A or C. All right? If I plug these values in, I think you get -2.16, but let me double check here. So 50 over square root. Yeah, you'll get that -2.16. Huh? So remember, if I'm looking at this formula, any test statistic I look at, my denominator represents the standard deviation of the statistic I'm interested in, right? Whether or not that's the average difference, whether or not that's the difference between two groups' averages, difference between difference between two groups' proportions, the denominator always represents the standard deviation, which we know variances and standard deviations always positive. So the sign of my numerator, or in this case, the sign of that average difference I find, that's going to be the sign of my test statistic. So because I found an average difference of -50, I know that either A or C have to be my test statistic. Yep. So if I do calculate it, you will get that -2.16. We'll do this last one before we go to. So just keep looking up kind of more critical values here. So if I've got this left-tailed test, just kind of reiterating once again, what should the sign of my critical values be for a left-tailed test? Yeah, I'm looking at the left side of that distribution. I know the middle of the distribution, it's centered around 0. So if I'm on the left side of the distribution, I'm looking at negative values. So I can rule D out right away. Okay. Now, one thing that you could do here, even if we don't want to look up this test statistic, think about these hypothetical values and think about if any of them make sense. Okay. So let's say I found the test statistic to be 2.5. Right? Instead of using the table here, I could actually just think about, do the combinations of these things make sense? So if I've got the very first critical value here of -2.3, right? So let's say I say that here's my critical value of -2.33. The rejection region for a left-tailed test, area to the left, right? Then I give you that assumed true test statistic of -2.5. Well, if the test statistic was negative 2.5, what should my rejection decision be? Reject. So 2.33, do not reject. That doesn't make any sense. I should be rejecting. What if it was instead 1.96? Well, the scale would change a little, but right, it would be kind of the same scenario. I should be rejecting. B doesn't make sense. The only one that even makes sense is C. Like if we're just looking, so I don't even really have to look exactly up that critical value. If I just look at the combinations here, I could have solved this one just by, does the combination of the test statistic and critical value, does that rejection decision make sense? So when I go to this one, negative 1.683, well, that would be, right, I guess, we're thinking about this critical value, be way out here, right, negative 1.683. My test statistic clearly in that rejection region. So yeah, that rejection decision makes sense. Okay. So even if I don't want to look up the critical value using the table, I can kind of test to see whether or not I can rule out a couple of these answers. In this case, I can rule everything else out except for the correct answer. But how would I find that negative 1.683? If I go up here, oh, actually this, oh yeah, I was gonna say, where's the alpha at? The alpha is 0.05. So we wanted 0.05 all in that left tail, and our degrees of freedom is what? Well, when we have a sample difference, right, our degrees of freedom goes back to not that crazy complicated formula, but simply, and kind of reminder here on the formula sheet for our sample differences, the degrees of freedom is n-1. So if I've got sample size of 42, my degrees of freedom would be 42 minus 1 or 41. I wanted 0.05 in that lower tail. So 1.683, but negative, right? Because I have a left tail test. Yeah. Yep.
If B, like, said reject, whatever, like, search my mind of the B, is that the right thinking process there?
Yeah, so if this was just reject, now we actually have to use the table because this one actually would have made sense. Like they would have lined up the rejection decision with the critical value in the test statistic. Yep. Yeah, it won't always be as nice that you can roll them all out, but that is the idea. Knowing those principles, you know, can make the questions easier and make it more likely you get the answer correct. Which that's how it should be, right? If you understand the principles, you should be more likely to get the questions correct. All right, I think we'll stop there, but are there any other kind of last, just a couple, like a small question for me before we get out of here? Like I said, I'll go over a little bit more in detail about the exam on Thursday. We'll just continue to do some review. I'll probably work through the rest of practice exam A and then kind of take questions. Like if you had an opportunity to look at the practice exams, ask me questions, or if you know there's some things you struggled on previous homework assignments or topics, feel free to ask open questions like, can you work through this? You know, can you fill in the blank? But I'll kind of be ready to kind of work for you guys on Thursday, whatever questions you have. And then once we exhaust those questions, kind of just finish working through some of this practice exam. Okay. Any questions for me before we get out of here? All right, I will see you guys on Thursday.